Yeah. Hello, everyone. We'll get started with the sixth session of RHPL. Thank you all for coming. Our first speaker for the day is Sylvia Kleza. Took me a time to learn this minute, but she's a professor at the University of Novi Sad in Serbia. And beyond, she's going to talk about subtyping and concurrent computation. She's also in applications of formal methods in many different areas, and some of them are policy for large-scale systems, machine learning, and open data tech. So you can also talk to her about that, maybe in the coffee breaks. Sylvia also won an award this year, 2024, for lifetime achievement from the Association of University Teachers and Scientists at Washington. So, Sylvia, thank you.
Should work now. Okay. Thank you for this kind introduction. I would like to congratulate to the organizers and to the PC chairs and program committee members for bringing together such an interesting program and for organizing and bringing us to this wonderful place. I will talk about subtyping and some research that I have done maybe the last 10 years, but also I am interested in applying formal methods in many different areas, and this is what we really can discuss. In India, I'm here within a bilateral project between IIT Delhi and Mathematical Institute of Belgrade. It is the co-PIs are Sanjeeva Prasad and myself, but at the end I will mention some future work about that. So this work on subtyping is done with a group of people, different people. Over time, the teams were changing, as you know how research goes. Young people join and then leave, and somehow the elder people stay. So it started with Mariangela Dezzani. We were working on subtyping in lambda calculus, and then moved to subtyping in session types with Nobuko Yoshida, who is actually one of the inventors of multi-party session types. Svetlana Jakšić, she was a student in Novi Sad. Jovanka Pantović, she is a professor in Novi Sad. Ivan Prokić was a student in Novi Sad. And Chester Skalas was a postdoc with Nobuko. He is now a professor in Denmark. So what are typings? We did not hear much work about typings and type systems here, but I will just remind you some basic facts. What are types doing? So when we have a language of terms which behave differently, there are sometimes infinite computations, there are sometimes loops. And if we want to avoid such kind of things, then we introduce types in this system, so in this formal language, in order to control the behavior of terms. The same things happen in programming languages. You are very well aware of static and dynamic typing. So mainly what I'm speaking here is about static typing. And in the field of concurrency of process calculi and concurrent computation, processes are the objects that are controlled by the types. So here we can see, on the left-hand side. So there is a term calculus, a lambda, a pi, or any other. And then sigma will denote the type. So these are objects that are assigned to terms. So in this sense, we assign types to terms, to programs, and to processes. What is the advantages? What are the advantages of typing systems? One of the advantages is, and maybe the most important advantage, is subject reduction, actually type preservation under reduction. So if we start, for instance, with a bool, and if we execute the program, we are sure that we will end up with a bool. We will not change to an integer. So a type system is guaranteeing such kind of consistency, which is called subject reduction. Also, termination properties. Most of the typing systems have termination properties, so they forbid infinite computations or programs that loop forever. In different settings, there are different good properties that are advantages, like progress, liveness, deadlock, and so on. However, there are, of course, disadvantages. There is no free lunch, right? So the disadvantages would be something like strict typing. We are very strict in typing. We do not have place for optimization of the computation, or we cannot do any reconfiguration in communication. However, this is a kind of trade-off, and we all know this famous sentence today that typed programs cannot go wrong. So no matter that there are disadvantages, we stick with this paradigm of typing programs. However, I will speak about these disadvantages and how we can the disadvantages, how we can somehow modify and make them less strict. One of the mechanisms to make a strictly typed system a bit less strict, to enable reconfiguration and optimization, is subtyping. Subtyping is a pre-order on types, so it's a binary relation on the set of types, and it is accompanied with a subsumption rule, which says, in the type system, which says that if a program is of type sigma and sigma is less than tau, then M is of type tau as well. So as you may see here, this less or equal gives this kind of flexibility. So we can assign more types to that program. I will speak, so this is actually some overview of my talk. I will speak about subtyping in concurrent lambda calculus, in concurrency in session types, and mention something about multi-party session types. So this is an ambitious program, but I will keep the talk high level without going into many details. In soundness, in subtyping, we consider something as soundness and completeness. Soundness and completeness are known from mathematics. We have many proofs of soundness and completeness. They are usually with respect to some semantics, some denotational, or some operational semantics. Here we will also see that there are two kinds of soundness and completeness, also denotational and operational as well. So two aspects of preciseness. Yes, so preciseness. What is denotational preciseness? So if we have an interpretation of types, for instance, of sigma, the interpretation of a type is a set of some objects, mathematical objects, and then the notational soundness is the statement that says that if sigma and tau are in the subtyping relations, that it implies that the interpretation of sigma is the subset of the interpretation of tau. This would be the notational soundness, and the converse is the notational completeness. So if the two interpretations are in this relation of subset, then the originals are also in the subtyping relation. What does completeness provide? As usually in mathematics, completeness provides the maximality of that relation. So completeness guarantees that this is a maximal sound subtyping relation. So any larger subtyping relation would be unsound. And as you may suppose, it's not always possible to prove completeness. The notational preciseness is the notational soundness and the notational completeness. And there are different results in the literature that deal with such kind of soundness and completeness for subtyping. It is also called semantic subtyping. For instance, this paper by Barendrecht, Coppo, and Dezani on filter lambda models. Let us move to operational completeness, soundness and completeness. So what does it mean that subtyping is operationally sound? It means that if sigma is less than tau, then objects of subtype sigma can be safely used in any context when an object of supertype tau is expected. This is the well-known Liskov substitution principle. So Barbara Liskov stated this substitution principle, I think in the 80s or something like that. So this here is a small example. For instance, if natural numbers are a subtype of integers, and if we have a context C, which expects the context C expects an integer, that we can replace, we can put a natural number there, and it will work since all natural numbers are integers as well. Operational subtyping follows from subject reduction of the type system, and this is one of the very good properties and consequences of subject reduction. What is operational completeness? It is the converse, so the inverse statement, meaning that if any object of type sigma can be safely used in any context where an object of type tau is expected, then sigma is less than or equal than tau. This is the converse. This is the operational completeness. And it is interesting that both in the notational semantics and in operational approach, only soundness was somehow researched. This completeness, this direction was not was not in the focus of investigation. So first, the reference on the bottom of the slide, but it is a paper, it was actually a technical report by Blackburn, Hernandez, Ligatti, and Nachtigall from 2014. They were the first to consider this completeness in a type system for iso-recursive types. Again, here, this completeness guarantees the maximality of a soundness subtyping. And it means, again, that any larger subtyping is unsound. So that is, yep. Yeah, exactly. Next slide. Okay. Okay, so here is your question. Yeah. So this story is a general story. As you see, I did not mention yet any system, but I will tell you the general story because now we did in different systems, we did these proofs, and we found out that there is a general method for proving this. And first of all, this can be proved by contraposition. So if sigma is not less than equal than tau, then there is some context in which any object of type tau can be safely used and causes error when some object of type sigma is used. So this makes, so there is some context which makes difference between sigma and tau. If we use tau, it is good, it is sound, it is safe. If we put sigma, then it is an error. So, so this methodology actually needs to address the following things. And the following things is we have to define, first of all, what is this negation of the subtyping. This is not always easy to define. In some contexts, it's easy, but sometimes. And then what is safely used? This depends on the context. In lambda calculus, it is convergence. In multi-partition is typing, and so on. Also, we have to define what is an error. It is also depending on the system, as well as we have to define what is that some context. We have to construct the context, and what is some object that is not behaving well in that context. And now I move to concurrent lambda calculus. It is a lambda calculus with two additional operations, with parallel composition and with the plus operator. I won't go into details. And what is the subtyping? So what are the types? These are usually arrow types, functional types with intersection and with union types. And again, what is the subtyping? Is a distributive lattice in which intersection is the meet, union is the join, and omega is the top. And the arrow satisfies these three conditions. These three conditions are, as usually as expected, with sets and with interpretation of sets. However, something that we would expect that holds, for instance, this inequality, this less or equal with union. Excuse me, this is a union and this is an intersection, so these are typos. Actually, this does not hold. It is unsound. We have shown that it is unsound. And now, in this context, with Mariangela Dezzani, we have defined these questions. So we have defined what does it mean. The subtyping is easy to define. Then its negation is also not difficult. To be safe for a context here, it means convergence. An error is a divergence. And we have provided some characteristic contexts, which are test terms and characteristic terms that behave exactly as the proposition says. If we move further to other calculi, so this was lambda calculus, distributed lambda calculus. If we move to other process calculi, such as pi calculus, CCS, CSP, yes? Yeah, well, this is because we have this distribution and I mean parallel composition. Mm-hmm. We have parallel composition and we have choice. Here is choice.
Okay.
So this is a distributive line. So this is an extended, it's not just lambda
No,
calculus.
just does the point one in the arrow satisfies?
Yes, the arrow satisfies, yes, but the rest is typable by this. It is, yeah, it is not,
Okay.
yeah.
Okay.
Okay, so if we go further to, yeah, to concurrency, to process calculi, where processes are our main object, it's not anymore terms or programs. Types that are associated, some of the typing systems, there is a huge variety of different typing systems. As you may see here in concurrency, there are different untyped calculi, as opposed to sequential computation when there is the lambda calculus. Here we have different, it depends on what we want to achieve and want to, in which environment we work. And there is also a variety of different types, they are called behavioral types that are typing process calculi. Here I focus on these two kinds of types, session types and multi-party session types. Session types have two participants, so the communication is here in the focus. It is sending and receiving messages, whereas where we have a multi-party session type, then we have different sessions which communicate, send and receive messages. So the advantages we already have seen. What is the advantage of a typing system? But here, what is even more important is that there is no communication mismatch. For instance, this cannot happen that that R wants to send to P and P wants to send to R. This is a communication mismatch because this cannot be evaluated further. Also, there are no orphan messages, so all messages will be delivered eventually. And here, what are the answers to these questions, to this general methodology? So, oops. No, okay. So this is again the story about soundness and completeness. And here in this framework, we have the Liskov substitution principle in concurrency, actually, which is a bit different from the one in programming languages, where types here are processes that are types. So this is for multi-party session types, we have proven soundness and completeness. This was the paper with Pantovic, Prokic, Skalas, and Yoshida. This was a POPL paper in 2021. In this general methodology, what we have, it was really a long work. It took several years. Of course, we did not work all the time in this area, but it was really a challenging program. It was very difficult to define what is the negation of the lesson of this relation, because here types are trees, infinite trees. Then you have to slice the trees and to match parts of the trees. So it was rather involved. But what we had here for good, very good, what does safe mean? Here safe means only typability. Because this paradigm, this is correct by construction. So if you can encode in the system, then you know that it is safe. And of course, we provided these characteristic concepts, contexts, and so on. This is the overview of the papers. So the first one was with Mariangela Dezzani. Then Mariangela worked with Nobuko and with Chen on the binary session types, and then we joined all together and worked on multi-party session types. This is the references. Our work is now within an EU funded project, which is called TARDIS, Trustworthy and Resilient Decentralized Intelligence for Edge Systems. In this project, we work on the verification of orchestration in federated machine learning using multi-party session types and CCS calculus. And what is ongoing, I come back, this is how I came to India, to New Delhi. We have this project with Sanjeeva, and we had a very fruitful discussion on session types, application foundations, and flow security. And hopefully that next year we will have to report something. Thank you for your attention.
Thank you, Sylvia. I'm not even. So in the interest of time, we'll restrict to about 3 questions. If there are any questions, I can recognize them. All right,
Yeah,
I'm glad we
maybe-
could discuss during your session and ask the questions directly. There have because of some technical errors, we are rescheduling some talks inside the session. So the next talk will be by Habib. Habib P is a PhD candidate at ISC. He is advised by Deepak D'Souza there, and he'll talk about approximate conformance in the context of deep neural networks. Let me just put it on for you. Yeah, over to you.
Okay, good afternoon. I'm Habib. I'm doing PhD at IISc Bangalore. I'm going to present our work on approximate conformance checking for closed loop system with neural network controllers. It's a collaborative work with Lipsi Gupta and Pavitra Prabhakar from Kansas State University. The broad goal of this work is to present an approach to transfer proof between evolving autonomous systems. So I'll start with the motivation to this work, and I'll explain the approximate conformance checking problem. As we know, traditional closed loop system consists of 2 main components, plant and controller. Plant model the dynamics of the vehicle, and controller will input the control input to the vehicle based on the current state of the vehicle to achieve some state or some goal. So traditional closed loop system uses controllers just PID or PA controllers. But in the case of autonomous system, these controllers are replaced or composed with neural network components. These systems are safe. Most of the autonomous systems are safety critical by nature of their deployment. For example, air traffic collision avoidance system, self-driving cars, etc. So giving guarantees on them is critical for the stakeholders of the system. The other challenges are these neural networks are continually evolving to incorporate newly available data or change the structure of the network to improve the performance or some other fine tuning. So verifying safety in the evolved system is a complex procedure. So we are going to present one approach to transfer proof from one version of the system to another version of the system. So this is a type of system. Let's say we have 2 versions of the system. Left one where the network is N1, and next it's evolved to a new network N2. Both start from an initial state. Our objective is to check whether the system is safe during the evaluation process. Broad approach is to transfer the safety proof from one system to another. So the clear way to check this is whether two networks are equivalent or exact conformance of input-output behavior of this system. For example, given two networks N1 and N2, we check for all input N1 of x equal to N2 of x. But this is a too strict constraint because after retraining or adding some more data to the data set, the weights may be different. So it is unlikely to satisfy. So we consider and we presented an approach. This is called approximate conformance of neural network. In our previous work, we showed if you have same input, output of two versions are bounded by some parameters epsilon. The two networks are said to be approximate conform if their outputs are within output difference are within some epsilon bound for a given input set. But this approach doesn't suffice for a closed loop setup. For example, let's say our two systems start from a given initial state x0. Then after neural network, we will get two output u0 and u0 prime. They are within the epsilon bound. Once we input these control values to the vehicle dynamics, we'll get a new state, two new states x1 and x1 prime. But these two states are different now. So our approximate conformance explained this paper is not sufficient to prove for a closed loop setup. So we introduce a new approach. It's called L epsilon conformance. L epsilon conformance bound the difference of output of two controllers in the presence of deviation in the input. And we also provide a global bound on the difference in the behaviors of two closed loop system. We also provide algorithm for L epsilon conformance of neural networks. And these two enable us to transfer proof from one version of the system to next version of the system. I'll explain this procedure. So what is L epsilon conformance? Given two neural networks, they are said to be L epsilon conformant if for the input that deviate at most by delta, the outputs deviate at most by L times delta plus epsilon. So L given two positive real values L and epsilon and an input set is N1 and N2 are said to be L epsilon conformant if for their output difference is less than or equal to L delta plus epsilon for all input values in the input set. For example, let's say we have two networks N1 and N2. We input x1, x2 to this network. If their difference, one norm difference, x1 minus x2 is less than delta, then we say they are epsilon conformant. Their output difference is less than L delta plus epsilon. Now, how do we quantify closed loop system behavior for in this setup? Let's say we have two versions of the system, and both start from a given initial state x0. We are considering simple dynamics, linear dynamics ax plus bu k, where a and b are some system matrices, and assume that both networks are epsilon conformant for some L and E values. Both start from a given initial state x0. Then this trace of the system, for the first system we have trace x0 to x4, and let's say eta 1 is the first system's trace. At the k step, the first system will be at the state xk. Similarly, for the second system, it will be at xk prime. Then the bound on the difference in the execution of these two closed loop system after k steps will be, we can compute the maximum difference by using this formula. Next, we need a method to check the L epsilon conformance between two networks. So we use a reachability based approach to check the L epsilon conformance. We construct given two neural network, we construct a new network N such that N outputs delta gamma, where delta is the difference of the inputs given to the two networks and gamma is the difference of outputs to the two networks. So essentially, we have two out for this new network has two outputs, delta and gamma. First one is the input, one norm of the input difference, and second one is the one norm of the output difference for a given x1, x2 that belongs to the input set. Once we have such a neural network, then the L epsilon conformance technique is reduced to a reachability query. We have two outputs, delta and gamma. Then these two networks are said to be L epsilon conformant. If for all delta gamma, the output of belongs to the output of the merged network, gamma less than L delta plus epsilon, then we can say that these both networks are L epsilon conform. To implement this, we need some gadget. First one is the append gadgets. This adds a desired number of layers to the network and they propagate the actual output of the network as it is without making any changes. Then second one is the difference gadgets. It will take two vectors as input and outputs the norm of the difference of the inputs. And third one is the merge gadget. It will merge two or more networks into a single network. I'll briefly explain the different gadgets. Input to the difference gadget is two vectors. Let's say x1 and x2. It's a assume that it's a two-dimensional vector. For first neural network, we have two input x1 and x2. For second one, x1 prime and x2 prime. Now we need to compute the one norm difference x1 minus x2. For that, we add a new layer to the network which will compute the differences. For example, the first node in the second layer computes x1 minus x1 prime. Similarly, the second node in the second layer compute minus of x1 minus x1 prime. Once we apply the value to these differences, we will get the zero absolute difference between these two corresponding nodes x1 and x1 prime. Similarly, for the second dimensional node also, we will do this. Finally, we will get the one norm of the output difference of these two vectors. I explain our merge operation by using an example. Let's say we have two networks, N1 and N2. X1 is the input to the first network and X2 is the input to the second network. In our merge, first one is the X1 network. We use append operation to make both networks have, to make sure that both networks have same number of nodes, layers. Let's say X2 is the input to the second network. Now we have two networks, N1 and N2, with N1 with input X1, N2 with input X2. Now we need to compute the output difference. For that, we use our difference gadget. It will output the one norm of the difference of the network, both this network. Similarly, we need input difference, one norm of the input difference. For this purpose also, we use our difference gadget. Then we use append gadget to propagate this to the output layer. Now the merged network, we have two nodes S and S prime. S will compute the delta value and the S prime will compute the gamma value. So now the L epsilon conformance checking is just a satisfiability query. We will just check L times S plus epsilon greater than S prime. If it is satisfiable, we say that these are not epsilon conformant, otherwise they are epsilon conformant. Now I'll explain the broad approach for the safety transfer. Let's say we have two versions of system, one with neural network N1 and another one with network N2. We first establish L epsilon conformance of two neural networks, then compute the bound on the difference in the execution of these two closed loop system by using our formula. Then we blot the reset of the first system by the bound, computed bound. If the blotted set is still safe, it is different from the unreachable, unsafe state, then the safety is established for the second system by using our method. Now I explain our experimental evaluation. we have a case study. It's an automatic rocket landing system. The goal of the system is to answer, the system will answer the control to a neural network at a particular height. The goal is to provide a smooth landing. And we trained various neural network controllers for different sizes. We also use some benchmark from this competition. And we implemented our method in Python and we used NNenum as a reachability checking tool. Now in our first set of experiment, the setup is we have different networks. We train different networks for the case study system. For different L and epsilon values, we evaluated the time complexities, check the L epsilon conformance. The observation is that it returns quickly if they are not, the input networks are not conformant, and it will take more time otherwise. The second set of experiments, we check the time taken to check the L epsilon conformance versus the network size. The results are it takes more time when the size of the networks increase. The third set of experiments, we compare the state deviation with actual state deviation and our state deviation computed by using our formula. Setup is we have closed loop system with same dynamics and different L epsilon conformant neural network controllers. And we analyze the actual state deviation with the theoretical bound on the state deviation computed by using our formula. Then the observation is that theoretical bound is close to the actual state deviation if the A plus PL is less than 1, where A and B are system matrices, and theoretical bound is greater than the actual deviation in the other case. In conclusion, we introduce the notion of L epsilon conformance between neural networks and used that to provide bounds on difference in the closed loop behaviors. And we provided a technique for checking the conformance by converting into a reachability analysis problem. We demonstrated the feasibility of the approach. As a future work, need to consider more complex systems and computing better theoretical bound, especially from A plus BL is greater than 1. That's all. Thanks.
Thank you, Habib. Are there any questions for Habib?
So, how do you come up with a good L epsilon for, let's say, a pair of?
That depends on the network. We have experiments in the paper for different L and epsilon. Depends on the system metrics and the network structure also.
So you have some technique to come up with
No,
search for a.
There's trial and error. But the bound depends on the L and epsilon.
Right, because the bound that you get will depend on how good your L and epsilon. So you're not stuck. So that as a network sizes grow to small time, so we also try to kind of do the safety properties independently on these networks and compose the solutions rather than creating these bigger networks and translating into a reachability thing.
There is some existing works. This diff and star diff. There are 2 existing works. We compared this approach with the in our previous work. We compared them with our approach, but they'll take more time compared to the reachability based analysis.
Okay.
In previous work, we compared them. If you do the separate reachable set computation and combined reachable set. Yeah, this approach is better than by experiment.
Okay.
Thank you, Habib. The next speaker we have is Elfie George. She's a PhD scholar at NIT Calicut. She's going to talk about counter abstractions for open multi-agent systems. This work led to a patent recently with its applications in vehicle surveillance. So congratulations on your patent. I just heard about it, and Elf will be talking. Thank you.
Good afternoon, everyone. My name is Alfie George. I'm a research scholar from NIT Calicut. So today I'm going to present the topic counter abstraction for open multi-agent system. This is a joint work with Shabana AT and Dr. S. Shirasuddin from NIT Calicut. First, I will give a brief introduction about multi-agent systems. So in multi-agent systems, a group of agents that will be interacting with each other or its environment in order to achieve specific goals. So the multi-agent systems can be of two types, swarms and teams. In swarms, the agents are homogeneous, that is, all the agents are of same type. Whereas in teams, the agents are heterogeneous, that is, the agents can be of different types. In this work, we are concentrating on swarms, but the result can always be extended to teams as well. Now we can look at open multi-agent system. In open multi-agent systems, countably many agents can join or leave the system at runtime. But if we take any particular instance of time, then there will be finite number of agents present in the system. Now we can look at open interpreted system. It is a semantics for reasoning about open multi-agent systems. It is based on interpreted system. Interpreted system is a standard framework for modeling multi-agent systems. So an open interpreted system consists of agents as well as environment. The agents will capture the behavior of individuals, that is joining or leaving the system, and environment will capture the rest of the system. So now we can look at agent and environment definition. So first, the agent definition. So agent can be defined by a tuple. A is equal to L iota act PT, where L is the set of local states that the agent can be in. Now iota is the unique initial state. Then act is the set of actions. Then P is the protocol functions. We have seen that agent can have local states and actions. Now, in each of the local state, which actions are possible? That information we will get from the protocol functions. Now, the transition function. So, given the current local state of an agent, the action performed by that particular agent and the action performed by other agents in the system and the action performed by the environment together gives the next state of the agent. We can look at an example of a train gate controller. So the scenario is a number of trains wish to enter a tunnel. There is a controller that coordinates the train entries through the tunnel for a safe passage of trains through the tunnel. Now here the agent is train and the environment is controller. Now we can look at the agent template. So the agent's local states can be outside, that is the train is in the outside state. Then it can be in the state of entering to the tunnel. Then it can be in the tunnel state and it can be in the collision state. Now here the initial state is outside, that is initially the train is outside the tunnel. Now the actions that is possible is approach, enter, wait and exit. And the protocol function here is from the entering state, only action enter is possible. Then from the tunnel state, the actions that is possible are wait and exit. Then from outside, wait and approach is possible. Now we can look at environment definition. It is similar to agent definition. It is defined by a tuple. E is equal to LE, iota E, active PE and TE. Here LE is the set of local state, iota E is the initial local state, act is the action, P is the protocol function, then T is the transition function. In the transition function of environment, given the local state of environment and the action performed by the environment and the actions present performed by the agents that is present in the system together gives the next state of environment. This is the example for agent template in the case of train gate controller. So here the environmental local state can be green, red and alert. So the initial state is green. Now the actions that can be performed is go, stop and alert. Now this is the protocol function. From green state, action go is possible. Then from red state, stop and alert is possible. Now we can look at the open interpreted system that we have seen in the beginning. So it has a tuple A, E and B. We have seen that A is the agent template, E is the environment template and B is the labeling function. So labeling function will be given to the agent's local state. Now in the case of train gate controller, the atomic preposition is safe and for entering outside, tunnel and exited, the labeling is safe, and for collision state it is null, that is unsafe state. Now one thing to note that whenever an agent joins the system, it will get a unique identity and that identity will remain unchanged whenever the agent has remained in the system. Now we can look at the behavior of this open interpreted system over time. So I have already said that if we take any particular instance of time, then there will be finite number of agents present. So consider there is n agents present in the system, then we can represent the global state as Gn. So Gn is the global state. So it is an n plus 1 tuple with local state and identity of each agent and the local state of environment. Now, initially, when there is no agent present in the system, only environment will be present. So the initial global state G0 will be the initial local state of environment. Now G is the set of all global state of any size. Now we can look at the transition in open multi-agent systems. There will be 3 transitions: agent joining, agent leaving and joined action. This is agent joining transition. In agent joining transition, a new agent can dynamically join the system and it will join to its initial local state. So the global state will expand to include the new agent. Here on the right hand side, we can see a sample global state. So in that only one agent is presented and it is in local state outside with identity 1 and the environment is in local state green. Now one agent joined the system. So now the global state become outside with identity 1, that is the previous agent. Now the new agent joined to the initial local state. So it is outside with identity 2, then the local state of environment. Now we can look at the agent leaving transition. So an existing agent leave the system. So here this is a sample global state. So only one agent presented, 2 agents presented in the system. One is in outside state and one is in tunnel state. So the agent with tunnel state left the system. Now this is the new global state. And in open multi-agent system, an agent can leave from any of its local state. So this is joint action transition. In joint action transition, the agents that is presented in the system and the environment together make some actions. So that is joint action. This is some sample joint action happening. So this is one global state. 2 agents present in the system. One is in entering state and one is in outside state. Environment is in green state. And the first agent is performing enter action and it is going to the tunnel state with maintaining the identity. Then the next state is in outside state. Then it is performing the wait action and it is remaining in the outside state. Then the environment is performing go action and it is going to the red state. So this is the transition function of train agent. I'm not explaining it in detail. And this is the transition function of environment in the case of train gate controller. Now we have seen what is an open interpreted system. Now we can go to the open model checking problem. So given an open interpreted system and a formula phi, we need to determine whether the system satisfies that formula. So here the formula that we have formula of interest is IACTL minus X, that is indexed to ACTL without the next operator. And this open model checking problem is undecidable, and it is proved in the paper Formal Verification of Open Multi-Agent System by Cuaros et al. So we were interested in the safety checking of open multi-agent system. So we identified a subclass of open multi-agent system where safety checking is decidable, and we can call this as regular open multi-agent system. So in this, agents can leave the system only from a fixed leave state. So in general open multi-agent system, the agents can leave from any of the local state present, but in regular open multi-agent system, the agents can leave from only leave state. So this is the modified agent template. So now initially it had only initial local state. Now it expanded and it have now leave state as well. And the protocol function of leave is empty set. That is, no action is possible from leave state. This is the modified agent template for a train gate controller. It has a new leave state called exited. Now we can look at the safety checking of regular open multi-agent system by encoding it into Petri-nets. So we can use the properties of Petri-net in order to prove that it is decidable. This is a brief introduction about Petri-net. So Petri-net is a 5-tuple PTFWM0, where P is the set of places, T is the transition, then F is the flow edges, then weight function, then M0 is the initial marking. Now we can go to the encoding. So corresponding to the agent's local state as well as the environment local state, we can give places in the encoded Petri-net. So these are in the train gate controller example, we have seen the local state of agent as well as environment. So these are the corresponding places in the encoded Petri-net. And initially G0, that is the initial global state, has only initial local state of environment. So that will be the initial marking. Next is we can look at the transitions. So first is the agent joining transition. So corresponding to agent joining transition in regular open multi-agent system, we can give a transition in Petri-net and it is connected to the initial local state of agent. Then for agent leaving transition, there is a transition in Petri-net and it is connected to the leave state. The next is the joined action transition. This is the same example we have seen. So corresponding to joined action transition, we can add a transition in the Petri-net. These are the pre-places. These are the post places for joined action transition. Now we can look at the correctness of joined action transition, correctness of encoding. So given a regular open multi-agent system, we can a run of regular open multi-agent system, we can construct a run of Petri-net. So this is one example. From the initial global state, we can construct initial marking, then so on. And we can come in the other direction also. Given the run of a Petri-net, we can construct the run of the regular open multi-agent system.
Only one.
Not necessary. Some agents can, it depends on the agents. If it want to perform an action, then it will perform the action. Otherwise, it won't. It will be in the same state. So every agent can have the possibility of taking an action and the environment as well.
So then how is the Petri-net transition model that?
This is only one joint action transition. So similarly, we can create as many possible joint actions and we can give the transition in that Petri-net. All possible joint action, that is possible.
Agents is unlimited, right?
But if we take any particular instance, then it is finite.
But how do you put the transitions? You have to put the transitions in the Petri-net up front, right?
Yes.
So how many transitions will you put? Maybe I don't understand the encoding exactly. Okay, go ahead.
Now we can look at the reachability. So reachability is decidable because in the case of Petri-net, the reachability is decidable. So it is decidable in the case of regular open multi-agent system as well. Then we can look at the safety checking of regular open multi-agent system. The safety checking gives that is we can say a regular open multi-agent system is safe if all reachable global state G from G0 is safe. So a global state G is safe if all the local state present in the global state is safe and except the local state of environment. Now we can prove the safety of this open multi-agent system using the liveness property of Petrinet, especially the L1 live property. So a transition T in a Petrinet is said to be L1 live if T can be fired at least one in some of the firing sequence in the language of M0. Now we can look at the proof sketch. So in proof sketch, that is, we are interested in the joint action transition. So this, okay. So in a transition, the transition in the encoder Petrinet will be in this format. That is, it can have the local state, the action, and the next local state. And from this transition, we can compute the unsafe transition. That is, if any of the next local state is an unsafe state, then we can call it as an unsafe transition. Then, if any of the unsafe transition is L1 live, then we can call it as the open multi-agent system. That is, regular open multi-agent system is unsafe. Otherwise, we can say it as safe. So this is some of the future works. We need to design and implement a tool for encoding the regular open multi-agent system to Petrinet. Then we need to explore the possibility of safety checking in general open multi-agent system. And we need to check the other direction as well, whether the Petrinet can be encoded into regular open multi-agent system or multi-agent system. If it is not possible, then we need to identify some subclasses of Petrinet that can be encoded into regular or multi-agent system. Then we need to identify some interesting subclasses of open multi-agent system and corresponding subclasses of Petrinets. Thank you.
Thank you, Elfie. Are there any questions? Seeing none, thank you so much. The next talk is by Mir Mohammad Sajid Sarwar. Sajid is a PhD candidate at Indian Association of Cultivation of Sciences, where he's advised by Rajoshi Ray. And he's going to talk to us about unsolvability of some planning problems. Connect.
Thank you. I am Sajid Sarwar. I am a PhD student in ICS, and today I will present our work explaining unsolvability for planning problems for hybrid systems through model reconciliation. So, Dr. Rajesh Roy and Dr. Anshuman Banerjee is my guide and collaborator of this work. So, before I start, there is a brief outline of this presentation. First, motivation of our work. Then I'll give a example planning domain upon which I'll elaborate my work. I'll show a hybrid automata representation of the planning domain. Then problem setup and our objectives. List our contribution. Problem statement for this work. Talk a little about model reconciliation approach. Present our explanation framework and elaborate with 3 examples, and finally evaluation and conclusion. So with the advent of AI, autonomous systems are now being applied in many areas of our today's life, And with this, need arises to explain the behavior of autonomous systems, especially in the safety critical areas. So we work on explainable AI for planning that I try to give explanation to the behavior of such systems. So what is explainable AI? It can be understandable with a simple example. Suppose an autonomous car is there and it carries passenger. So the decision taken by that car, like changing the route or visiting a refilling station, these decisions need to be understandable to the end user. So the crux of our explainable AI is that the AI agent of the autonomous system should give some sort of explanation along with this decision to the end user so that it is understandable to the human user. An application of this area is we can build trustworthy, transparent systems as well as in the pre-deployment phase, we can to meet the system behaves as desired behavior to ensure that. So here is an example. I will start with an example planning domain. So consider a warehouse automation where a robot arranges the consignment within the warehouse. So the topography of this domain is partitioned into some cells. There are some block regions like the gray cells are the block through which the robot cannot pass through. The orange cells are actually the worn out surface where the robot depletes more energy than the regular surface. And the green location 22 is the recharge station. And the planning problem for the robot is, which is initially at cell 7, to carry the consignment, the black box, to the goal location that is 18. So in our work, we assume that the human and the AI agent both have its own knowledge base. And we assume that the AI agent has the correct knowledge about the environment, whereas the human doesn't have the full knowledge. It has partial knowledge or erroneous knowledge. And we model these, we model these two different knowledge base as hybrid automata. And in the hybrid automata, it encodes a continuous as well as the discrete behavior of the system. So the each cell can be represented as a symbolic location. Here, the square box are the symbolic location representing each of the cell of the warehouse, where the continuous dynamics here is the robot movement and the energy depletion, which are given as the flow condition, are encoded as a continuous dynamics. And cell to cell transition of the robot is encoded as a discrete transition. For space constant, we show both the automata in the same figure. The reference here is in the red lines. It is actually, if you remember the previous figure, the cell 20 is the agent knowledge. It is actually a obstacle, but human assumes that it is a free cell. So here you can see the transition from 19 to 20 and 20 to 19. Similarly, 20 to 21, those are the invalid transitions that human wrongly assumes. As well as the flow dynamics of cell 16, location 16 and 10. You can see the red, the flow rate of charge depletion is difference is shown in red color. So in our problem setup, we have domains with location and transition. We have an initial configuration, we have a goal configuration. It captures both the discrete and continuous dynamics. We have agent knowledge base, which we assume that it has a complete knowledge. Human has a partial or erroneous knowledge of the domain. And what is required is a plan from the initial to the goal. And we assume that the planning problem is actually unsolvable to the agent, but it is solvable to human knowledge due to its erroneous assumptions. So what is needed is that the AI agent must explain why the planning problem is actually unsolvable. And in this process, the human updates is knowledge base. So here we list our contribution here. We build a model reconciliation framework to aid human to update its knowledge base. This work leverages the reachability analysis, intersection of reachability analysis and planning. And I will explain how we do this later. And we use a path-oriented reachability analysis, where each path is represented as a linear constant set, and we satisfiability of that constant set implies that the path is actually reachable. But when it is unsatisfiable, then it implies that it is actually unsatisfiable path. And we, for an unsatisfiable path, we actually extract the minimal infeasible constant set that actually causing the unsolvability, and that is given as a reason for unsolvability. So in our work, a planning problem for hybrid systems is a tuple which has a domain which is represented as a hybrid automata that we have shown. Problem has a initial state, initial configuration and a goal configuration, and it is a depth. There is a depth for the plan. In other terms, in how many steps we are assuming to the problem to be solvable, or in other words, how many actions can be applied to solve the problem. So a plan for a planning problem is a sequence of action. And action, action is a discrete state transitions, discrete state transitions from initial to the goal that lead the initial state to the goal. So consider this example. In this example, a plan is shown as a dotted line, and so we can say that these are the discrete state transition from 7 to 18 is a plan, and we can map this plan to a path where we also, if we consider the graph structure of the automata, we can map the plan to a path where we also bring in the location information here also. So the problem statement is that given a human model and a agent model and a unsolvable planning problem instance, the model reconciliation problem is to provide a update model update so that human can understand why the planning problem is actually unsolvable. So in model reconciliation, we have two models, human model and agent model. Agent model is the gold standard, where human model is not. So a path-oriented reconciliation process, the agent should give some sort of update to the human, and human update is knowledge base. So here is our explanation framework. We take two automata, human automata and the agent automata, and the problem instance and plan depth as input. We first compute the graph structure from those automata, GA and HA, and in the human graph, we first construct a path there, and we try to display the path first in the discrete in the graph structure of the agent graph. If it is replayable, if it is not replayable, we identify the infeasible transition that is actually not present in the human graph. And if it is feasible, then we first, through reachability analysis, we first check the feasibility of the path in the human automata itself. We bring in the continuous dynamics here and check the feasibility of that path in the human automata. If it is not feasible, we just discard that path. But if it is feasible, we then check the path in the agent automata with the continuous dynamics. And as the planning problem is unsolvable, that path must be infeasible, and we find irreducible infeasible set or minimal infeasible set to of that linear constant set. As explanation, we map that constant set to a path segment and return that path segment as explanation for unsolvability of that path. So there are three examples. First, you can see a plan in the human model. Now, first we replay this path in the agent model in the graph structure, and you can see that it is stuck in the location 19 as location 20 is a obstacle. So we identify an infeasible edge here. Now consider the second path. In this path can be successfully replayed in the graph structure in the agent automata. Now we check the feasibility of this path in the human model first. We bring in the continuous dynamics. We encode the path as a linear constant set and checks the feasibility of this path. And we find that this encoding is a standard technique already available in the literature. So I am not going into the details. So we found that this path is actually infeasible in the human automata itself. So we just discard this path as infeasible path. Now consider the third path. This path is replayable in the agent graph. It is feasible in the human model. Now we are checking it is in the agent automata with its continuous dynamics. Now we found that this path is not feasible there, and we identify the IIS subset of this linear constant set, and we found that these are the locations whose constants are actually causing the unsolvability of this path. In this work we only for a linear constant set we only identify the IIS subset of it and map that to the path segment. We did not look into the continuous dynamics of the problem. That can be a future work. We have already started a work where we are going to look into those continuous dynamics of those segments like location 10, 16 and 12. Where actually the problem is arising. So here,
is there some obstacle in one of the cells on the path, or
actually the problem here happening is that charge depletion rate is in these locations is higher than the normal cells. So it is abruptly reducing the charge of the robot.
okay?
So we map that IIS path into the segment, and we do this process for all the possible paths in the automata and collect all these IIS segments. And here is our result. We perform our evaluated our framework in two benchmark domains. And you can see here it is quite small, but in the first table you can see that we have done in different planning problem instances as well as in for different plan depth done the experiments, and you can find that here is the number of locations in the automata. This column represents in the human model how many number of transitions they are in the human model. This one is in the agent number of transitions in the agent model. Here number of path we have explored for a plan depth, and here you can see the number of infeasible paths that we have collected, and this column represents the accumulated time to do all these operations, and here is the memory. And the second table here you can see that on average to generate explanation, the average time taken by our framework. So I like to conclude here. In this work, we propose a path-based continuous model reconciliation framework, and it shows that discrete and continuous path analysis approach can leverage to drive explanation for unsolvability. We demonstrate our framework on two different benchmark, and we show that the average explanation generation time for our framework is quite small, significantly small, and um, and um, and most of the cause of unsolvability is tracked by the framework. So that's it.
Thank you, Sajid. Are there any questions for him?
So I didn't understand the problem correctly, but why doesn't the agent just tell this is the example role? Why does it?
You're saying that the whole model. Uh, yeah, it may be costly to send the whole model as a update.
Mm.
And another reason can be human and agent both acquire the knowledge with uh, uh, with exploration. So maybe agent also don't have the full knowledge. It is exploring and gathering knowledge, and human are also gathering knowledge. So in consultation, they both build uh, their knowledge base.
Okay.
Any other questions? Seeing none, let's thank our speaker once again. Thank you, Sajid. And our next speaker is Diganta. He is at TCS Research and used to be at CMI. He did his BSc and MSc from CMI, and he's going to talk about learning DNN abstractions using gradient descent. This work was published at Automated Software Engineering earlier this year. Set up the slides. So, yeah.
Stop sharing, but then it should.
Let's try window once more. Okay. That's it. Oh, this slide progressing में थोड़ा delay आएगा ना. Okay, sure. So we have slides, fine. All right. So sorry about the technical issues. Bear with me for a second. It's probably not entirely full screen, but let's maybe go ahead with the presentation given the current delays, if that's okay with everyone. Yeah. So yeah, so this is work is called learning DRN abstractions using gradient descent. This has been done by me and several collaborators, Sana Siddiqui from IIT Delhi, Rishikesh from TCS Research, Madhukar, who is in the audience with us, and Guy Katz. Yeah, so let me go ahead. So firstly, I'd like to motivate a bit about why we want to do neural network verification at all in the first place. I think you probably don't need any motivation for this, but nonetheless, I mean, neural networks are being used in several safety critical applications, and there are several such applications where really you can't use any other systems, right? Like for example, if you want to detect objects in a room, you can't use any other system. And yeah, we have seen several domains in which neural networks are really being used, and we don't have any other alternative solution. And similarly, there are several safety critical domains in which we only know that nothing else works, but neural networks also doesn't really work because we're not sure about their safety, right? So things like some analysis of medical images, automated analysis of medical images for diagnosis, for other purposes. Neural networks may or may not, we don't know of any other technique that will work for this, but even with neural networks, things like robustness is an issue, right? So this is a classical example from a paper I think it was some 2017. What they did was they took a stop sign. They took the then state-of-the-art neural network for detecting traffic signs and some pieces of tape on the right. So imagine if there was an actual self-driving car that has been, trained on some of these stop signs and has got a neural network as a part of it somewhere, it can completely get derailed, and this can be a really unsafe situation, right? So we would like to somehow verify and avoid situations like this. So verification is needed. Yeah. Okay, so what is a neural network? Cool. So yeah, probably correct. Yeah, yeah, yeah. So how do you do focus on content over here? Do you know? I mean, basically, this needs to be removed this time. Correct. Thanks. Is this good? Okay. Yeah, so I think most people know what a neural network is. In the interest of time, I think we're already learning late. I'm just going to quickly skip this slide. So we're working with ReLU DNNs. So we don't look at other activation functions as of now. But the main thing is that DNNs are really, really hard to verify. And we can look at this fact in many different ways. Of course, there are many neurons, many layers. They've kind of nested if then else statements. They're hard to slice. It's not really evident that there's a part of a network that's doing some part of something. So you can't do divide and conquer kind of things. Of course, it's NP hard. So from a complexity point of view, we know that it's a hard problem, right? So how do we deal with this? So there are some solvers, right? There's some specialized solvers designed to deal with neural networks. Marabu, Alpha Beta Crown, Neural Sat. So three solvers I've chosen, which seem to do fairly well on the benchmarks and have various different techniques, but scalability remains an issue across these solvers, generally speaking. Okay, so what do we do then? We do abstraction, right? So whenever we have scalability issues, the natural solution we go to is abstraction. So what does abstraction look like in this context? There are various different techniques involved, but I'm going to focus on structural abstraction. But generally speaking, see, we want an over approximation of the behavior of the neural network. And what should this over approximation be? It should be sound. It should not have too many spurious counter examples. It should have as few spurious counter examples as possible. Ideally, not any, but that's probably not going to happen. And it should be efficient. In our case, efficient just means that it should be a small network. So what we want is, given a big network N, we want to find an N prime which satisfies these kinds of properties, right? The behavior of N prime should somehow over approximate the behavior of the original N, and it should not introduce too many spurious counterexamples. It should not introduce, it should be small enough and so on and so forth. So how is this done, right? Okay, to simplify things a bit, I'm going to make some assumptions that N has got only one output and that we are only interested in an output side property of the form where we have y less than equal to c and so on. So in this case, if that's the, so this kind of soundness and no counterexample conditions simplify a bit. So now we are only interested in an N prime, an abstract network, whose value should be greater than the existing concrete networks, right? We don't have this general kind of implication thing. We are only interested in an abstract network whose value is going to be greater than the existing concrete networks. And then, of course, this condition that there's only a very few spurious counterexamples, this also gets simplified somewhat. We are now only saying that that there should not be a case where a counterexample is, a point leads to something greater than c for n prime and less than equal to c for n, right? And we assume some conditions in the precondition, and again, things simplify a bit more, but we don't need too much of these details. The important point is that this is a general transformation. And this has been shown in a fairly old paper from Elbor and Geikatz and others in CAV 2020. So given that this is a general transformation, you can always do it by adding layers to the beginning and end of the network. So there is, you're not losing anything by doing this. For the sake of the talk, I'll also assume that the network at hand is safe. There's equivalent things you can, like, there's things you can do when it's not actually safe, various points in which you can terminate. But if it is safe, then this condition that there is few spurious counterexample really reduces to there should not be a spurious counterexample in the abstract network, right? Because there a counterexample in the abstract network is only can be spurious. Okay, so here is some of the existing DNN abstraction techniques. Several of them are quite interesting, but they all have certain common kind of gaps. And I would like to take the next few slides to describe one of these techniques and the gap in those techniques, and that will kind of apply for most of these as well. Okay, so I'll talk about this split and merge framework from this CAV 2020 paper that I linked to some time back. There are several techniques which are based on this framework, and there are also several orthogonal techniques that have been developed, but all of them follow this kind of a cigar pattern, and all of them look at merging neurons in one way or another. In particular, this split and merge framework, what it does is that, see, once we have this property that we are only interested in upper bound of the output of the network, what we really want to do is we want to somehow prove that this network, this output neuron over here should only increase, right? So we'll mark it as so. We'll say that this is only allowed to increase. I don't know if this blue text is visible, but it says increasing. Okay, this is only allowed to increase, right? So then immediately we know that this neuron can only increase because it's connected by a positive edge. If you increase the value here, the value here only increases. Similarly, we know that we are allowed to decrease this red neuron over here, right? So if you decrease the value here increases, right? So we have this kind of a relation immediately established. Now, as we progress, we can keep going back one layer at a time and marking things as ink and deck and so forth. Unless there is a conflict. So, for instance, in this brown neuron, in this lower side of this middle layer, this brown neuron here, this can be marked as increasing according to this edge. It can also be marked as decreasing according to this edge, right? So it's not clear that if you increase it, it will only lead to an increase or a decrease of the final output value. So what do we do in such a case? We split. So we split this into two copies. Each of these copies is doing exactly the same thing, but the output weights are now kind of split between them. And if you do this now, you can unambiguously sort of label them as increasing and decreasing, right? So we have this split of the network, and now we can go ahead and actually start merging things. How? Well, see, now that you know that this neuron is, both of these two neurons are increasing, you can make a particular transformation. So take this 1 and convert it into a 6 so that it matches the 6 on this particular label, right? Similarly, take this -5 from the previous slide and convert it into a 2. So notice that this transformation is only going to increase the value of these neurons. We are allowed to do that from the point of view of that's only going to create a more over approximate network, a sound over approximation. But once we do this, both of these two neurons are calculating the exact same function. They're calculating 6 times whatever this guy is plus 2 times whatever this guy is, and so on and so forth. So both of them are calculating the same function. There's no point in keeping 2 copies. We can just merge them, and that's going to be an exact operation. Right, and that is exactly what we do. And similarly, you can merge the red neurons and you get a smaller network. Now, this network, once you do all of this, the value at the output is only going to be greater than whatever the value there was in the beginning, right? So if you know that this network doesn't violate the upper bound, the original network doesn't violate the upper bound, right? Okay, so this is great, but how do we choose which neurons to merge? We can merge these guys, we can merge these guys. There's so many different choices. In fact, the choices will very naturally give you a partial order of all the possible merges you can do. And most techniques, what they do is they do some kind of a cigar-based search along this partial order, right? So what does this partial order look like a bit more concretely? So all of these are various abstract neurons you would get, abstract networks you would get for various different choices of merges. Some of them are actually strong enough to give you the proof. They don't have any spurious counterexample. So those I have labeled as green. So that's the lowermost one and this green one, right? This top one corresponds to merging everything to one. So this is the most coarse abstraction you can get. The bottom one similarly corresponds to not merging anything. So it's basically the original network, right? And then there will be some things which lead to some proof. A cigar-based technique will not start from the top, start from merging everything, and it will get a spurious counterexample, let's say, and it will go down this, this partial order. So it will unmerge some things and get to something smaller. It will unmerge something more and get to something smaller, and it will go down this until it gets to somewhere that's green. As soon as it gets to somewhere that's green, we have a proof. Right? So all of these are going to be solver queries. So we want to minimize the number of searching we do, we want to minimize the number of steps and so on and so forth. Most importantly, we want to stay as high as possible in this partial order because those are smaller and more efficient networks, right? For example, what we don't want is a situation like this, where we take this kind of a step, we go to N1 prime here, and then go here, and then go to the original network. Here we are only able to prove once we have refined all the way back to the original setting, right? So this is the most suboptimal thing for us. But notice that if I ever come down to N1 prime, I can never reach any green region that's not the original network. So if in the first step from this N top, I make this kind of a transition, I'm already stuck. I cannot reach these green regions, right? So here is a situation where, no matter what your heuristics are, no matter how you're using counterexamples to refine things, CIGAR is not going to actually be able to give you an efficient abstraction that is able to complete the proof for you. So this is kind of a situation where you can get stuck. And what we observe with these existing tools is that if you play around with them, oftentimes there are situations where you have to go all the way to the end, right? So we suspected that this is really what's going on underneath. Okay. So this is one issue. The other issue is there are unread which are really represents efficient abstractions. So consider this network. Again, you don't need to parse all the details, but just look at the plot over here for a second, right? I take my word for it, but this network, it does produce this lower blue plot over here. So this blue kind of region is precisely how this network is going to behave. It's got 2 inputs, so there's a 3D plot and so on and so forth, right? Now, if I want to prove an upper bound of 2, notice that this green region, if I get a network that behaves, whose behavior gives me this green region, that's good enough for giving me an upper bound of 2, right? Yeah, so the plot is there is x0 and x1 along these axes. So these are the 2 inputs to the network. And the output y0 over here is basically the value that the network is outputting, right? So the way that the network is going to behave is that within this region, the network is going to output values that are going to lie on this plane. Within this region, the network is going to output values that are going to lie on this plane, and so on and so forth. This is a fairly low dimensional example, so we can actually directly plot it. Of course, in larger networks, this won't be the case, but this is just for visualization's sake. I mean, kind of a motivating example, if you will. Right? And what we want to prove about this is that ultimately the value should be within 2 for some input bounds. I mean, when input is between 0 and 1, output should not be greater than 2, right? I mean, of course, in this case, you can look at it and tell that this is the case. But what we want is an abstract network that can prove this, right? Okay, so what could be one such abstract? There would be many, but look at the green plot. If somehow I can get a network that gives me this green plot, then I'll be able to use the network to prove this. And what I claim is that there is a network that produces the green plot, right? But that this network is not reachable by doing any kind of merging that I was showing in this previous thing. So all of the existing structural abstraction techniques, we are going to do this kind of neuron merging, but that can never give me this kind of a green network that can give this green plot and that can give a efficient proof in this particular case, right? So this is an example where no matter what heuristic you use, no matter how you search through this space of abstractions, if you just do some merge, it will never kind of give me, yeah, time check, good. So that's 20 minutes remaining or done? Cool, good, okay.
Some other merging that you can get, which gives you this flexibility that is less than equal to 2.
Sorry, I couldn't hear you. Can you come again?
So there is technical.
Yeah. So I mean, so is the question: can I reach to this network at all efficiently?
To this network, you just want to show the connection, right?
Correct. Yeah. So I mean, yeah. So the question, if I understand, is that why you want to go via this particular? So I'm saying that, yeah. I mean, if in this particular case, I don't go via this network, all the other merges that I can do that give me 2 neurons are not strong enough to prove the post condition. So what I'm not saying is that we need to go via this. What I'm saying is that all of the other techniques, they don't go via this and hence are not able to handle this example. We are able to handle because we go via this. So that's the kind of thing. And so, I mean, you're getting to a very interesting point in the sense of, do we have something strongest? Do we have how strong, like characterizing how strong the abstraction, expressibility of the abstraction is, if you will. That's a good question. We have not explored that too much as of yet. But yeah, this is a working example where we show that there is a difference. There is a gap between the existing things and whatever we're doing. But yeah, there's the precise characterization is not in place yet. So, okay. So then, yeah. So what I'm going to now do is somehow come up with this network, right? And I'm going to give a general technique which will be able to come up with this network. So what we saw was we saw kind of 2 limitations of the existing space. One is that, of course, this unreachability issue that optimal n prime might be unreachable. The other is that CR might get trapped somewhere, right? In the sense that if it makes a bad decision, then it gets trapped. And this is something that we've explored various kinds of heuristics based on various kinds of things where it's kind of hard to make CR guide. And I think I'm kind of low on time, but I'll quickly talk about how we handle this. The way that we handle this is we'll come up with a parameterized abstraction, and then we'll do gradient descent on top of that parameterization, right? So let me quickly sort of talk about that. Okay, so 2 steps: parameterized merge, and then we'll do gradient descent on that parameterized, abstract network. So the first step is to somehow construct this parameterized abstract network. Now, what we noticed in this previous example was that the reason that we were able to get this and nobody else was able to get this is that the 2 neurons A0 and A1 somehow share responsibility of abstracting the same underlying concrete network, which is not there in the previous cases. In the previous cases, you were taking a bunch of things and merging them together. So each concrete neuron was only being handled by one abstract neuron, right? Whereas here, there's some sharing of responsibility going on. And to sort of achieve that, what we're doing is we're going to take the concrete neurons and we're going to create these copies and multiply their values by lambda. We ensure that the values that we multiply the output by sum up to 1. And if they sum up to 1, then it should, this step is going to give you an exact, the same exact behavior of the original network. Then we do some weight replacement. So we had started out with the original network, made 2 copies, C01 and C00, multiplied it by lambda. And now we're going to do some weight replacement where we are going to make sure that the incoming weights of these 2 guys and the incoming weights of these 2 guys are exactly the same, right? So now we can actually, we have a situation again where these 2 are calculating the same function, these 2 are calculating the same function, and we can, similar to before, merge. And if you follow these steps, this is the network we get back, right? Which is something that was not, reachable previously. So notice here that all of these operations, the only thing that is actually, so firstly, all of these operations, they have 2 parameters, this lambda and the weights that we're replacing things by, right? And the only thing that is not necessarily sound is the weight replacement. When we're making the copies, no matter what the value of lambdas are, they sum up to 1, right? So we'll get the exact same behavior. And no matter what the values are, when we do a merge, we get the exactly same value. So only this step is where soundness needs to be taken care of. Taking care of soundness is again some details, but this is the condition that needs to hold. What we do is we relax it to sort of condition that looks like this based on this particular value of delta. The interesting thing is that this optimization problem can be solved fairly easily in constant time. And in terms of code, it can be solved in a way where you can actually write it into a loss function. So this whole optimization, the solution to this optimization problem can be something you can do gradient descent on. Therefore, this whole condition in the bottom, you can always ensure that this holds. And then you can propagate the values of delta accordingly. So soundness always holds because of this delta, because of adding in this delta. And we have to do this because, otherwise just making sure this condition holds when you're just doing gradient descent for some abstract W prime is hard, right? Yeah. So then finally what we do is we have this parameters abstract network where you have lambda and W prime. And we want to do some sort of a gradient descent based search over this. And what we want to make sure is that we want to make sure that there are no spurious counterexamples, which means this condition should not hold, which means this value should not be large, which means this loss should be small, right? And then we can estimate this expectation via some sort of random sampling. Okay, so this was the technique. Before I go into experiments, are there any questions? If I'm already out of time, I can quickly describe the experiments. This is the table, but yeah, I mean, this is pretty much the end of my slides. Open to questions. Yeah, so
Thank you, Digon. We can take maybe 1 or 2 questions and then. Okay, great. Seeing none. Thank you, Digon. Business meeting has actually started, which is why I was rushing him a little bit.
Yeah.
The business meeting has started across the hall in 101, if you'd like to join. I don't know about tea break. But yes, okay. I think there might be tea break concurrently, simultaneously at least.
I'll just stop this, I guess. Stop sharing. Yeah.
Excellent talk.
Thanks.
So, yeah, like, why is it? We will talk later. So,
Yeah.
Go check. Very cool work. This was Madhura, right?
Yeah, this. Because up there.